in Stat 241, we are covering a lot of material at a very shallow depth. So just keep in mind, sometimes we might just say, you know, this magically happens until you actually take some more mathematics and statistics courses and understanding the math behind it. You're welcome always to come in during office hours if you want me to go into the why and where it comes from and how you do this longhand, that kind of stuff. But overall, the course and kind of the big idea of the course, we're going to start with descriptive statistics. It's kind of its own branch within statistics. You are describing sample data usually, maybe graphically or in a table or some type of numeric response like the average. Those are all descriptive statistics. And then we're going to move into probability. It is necessary to look at some basic probability to understand the next section. So we're not going to be very heavy in the probability like our counterpart, Stat 243 spends a lot of time on probability. We're going to just brush the surface of probability, mainly so that we can use those probability tools in inferential statistics. And that really is, I think, the interesting part of statistics is what we do is that we use these descriptive stats and probability to infer what's going on in our population. So that's where more of our research methods, things that you can actually set up an experiment and measure that experiment and see if that experiment is causing some change from medication, predicting some stock market crash, those kind of things we could use inferential statistics for. When we are measuring a population versus a sample, we have different names for those things. So talking about, we have some population. And the population doesn't have to be everybody in the world or everybody in the United States. It could be just freshmen in college or freshmen at PSU. It could be dogs. It could be anything that you want as your population. So don't keep in mind that it has to always be the entire United States when we are looking at our population. Usually the population is difficult to measure. We try to capture, for instance, everybody in the United States with a census every 10 years, but we never capture everybody. We leave out homeless people. We leave out people that are just obstinate and don't want to answer the census. There are people overseas that may not have access to that census in the mail. So there's ways that we try to measure the population, but it's expensive, it's very time-consuming, even to do our census every 10 years. So what we do is that we take a sample out of this population, and we'll talk about different sampling techniques, but we're going to take a sample out of that population somehow. We're going to measure that sample using descriptive statistics. And then, so open the arrow that way. Then we are going to take our sample and infer back of what we think is happening in that population. So if you do a good enough job representing your population with your sample, then that information, that inference that you bring back to it should actually hopefully give you correctly what's going on in that population. If you take a bad sample, though, then it's not going to correctly predict what's going on. For instance, a lot of the election results from our last election did not identify the correct candidate winning, and most of that because it was taking a popularity vote. It wasn't taking an electoral college sample from each of those districts and stratifying it in a way that you represented each of those electoral outcomes correctly. So you have to be careful on how you take these samples. Unfortunately, a common way to sample is something called a convenience sample. Just because it's convenient doesn't mean it's probably a good idea. There are things that we have, well, I only had access to a popularity vote, so that's why I'm polling that when you're going through from internet polls. Maybe I'm doing some marketing and I only have access to a particular store like New Seasons. I may not want to use those results to go back to something like Winco and predict what the sales are going to be for a certain item because you have a different demographic. that might be using those two different stores. So you have to be careful about types of sampling that we're going to use. But we're describing our population with probability. And then our sample we're describing with descriptive statistics. And I'll put here the first of our two vocab words when you're talking about is the difference between parameter and statistic. And the main difference there is that our parameter is some type of measurement of the population, and our statistic is the measurement of the sample. So when I say an average, we could have a population average, that's the parameter, or we could have a sample average. So again, it's really hard to measure the entire average of an entire population because we don't have that data available. So we take our sample, we find that statistic, the average, and we use it to infer what the parameter could be. That's like kind of our goal in this class, is to describe these statistics and use them for inference on the population. But we need to have some idea about what that population looks like. So that's where the probability theory comes in. So we could look at maybe a simulation of what's going on in our population. With powerful computers now, that's actually much easier to do. We could just make assumptions about our population based off of known. We have different notation that we're going to use for these parameters and statistics. It's important that you actually start memorizing what these symbols stand for. So on the left, I'm going to write down the symbol for the parameter, and on the right, I'll write down the corresponding symbol as the descriptive statistic from your sample. And then in the middle, I'll talk about what they are. So the first one that we're going to talk about is called the mean. Our parameter, the notation that we use for that, is a Greek letter M, but it kind of looks like a cursive U with a longer tail on the bottom left. That's pronounced mu. When you see this symbol, you just have to know that it stands for the population mean. And I'll put, again, this is population, and this is your sample. When we are working with a sample and a statistic, the notation that we use is called X bar. And the mean is just your regular average, where you add everything up and divide by how many you have. And this one we just say X bar. That's how we say it phonetically. There are many different types of averages, though. But when we talk about the mean, in this course, we're just talking about add up all the data, divide by how many items that you have. So just your regular average. Another one that we work with quite often is called the variance. The variance is a way to describe how spread out your data set is from that average that we're working with up here. The symbol that we're going to use is another Greek letter. Think about kind of like a slanted 6 almost, but you have a 0 kind of with a tail off on the top. And then we're going to square that value. And it's called, so phonetically that would be pronounced sigma squared. Sigma, this is the lower Greek letter S. I know it doesn't look like our S's, but it is a Greek letter S in lowercase. Sigma squared is the symbol for the population variance, the measurement of the parameter. The sample variance that corresponds with that is called S squared. Now that formula page that I'll put up on the announcements has a list of these. So you don't feel like you have to necessarily memorize them, but it is helpful if you're taking notes when I say the population variance. If you get comfortable enough by writing just sigma squared rather than that whole word population variance each time, it will help you with shorthand. And also, as you read through the textbook, there are going to be some equations that pop up later on that might have all four of these symbols in the same equation. And you'll need to know the difference between one coming from the population versus one coming from the sample. But in general, the Greek letters are used for population, and the Roman alphabet is used for our regular sample statistics. That's not always the case, but they usually keep that pattern. Another one that we're going to work with is called the standard deviation. It also measures how spread out a data set is, but it's a little bit more useful than the variance. They're related. It is just the square root of the variance. So we would just, instead of the squared symbol, we use the corresponding symbol without the 2 next to it. So we have just sigma and just a regular S for our standard deviation. Proportion. We're going to use a lowercase p for proportion and a lowercase p with a bar over the top to stand for the sample proportion. Some books will use pi here to keep with the Greek letter, but pi in mathematics actually means a number 3.14 approximately, so we usually, that's the one case where we don't to drop back to the Greek letter just to make sure we don't confuse it with the number pi. There will be more, but those are the main ones that we're going to work with the beginning chapters. The main thing here is to keep in mind that when we're describing our populations, we have a hard time actually calculating these numeric values. Your book will give you formulas for these. But again, if I wanted to calculate the average of the entire population, and how many billions of people you're going to add up their age and divide by to get to that is pretty intensive if you even have access to those records. Now, sometimes we do. Like, for instance, we probably have everybody's age here at PSU in the system. So we could probably do a population average of PSU students. Or maybe everybody taking some type of standardized test, like the GRE or SAT or ACT test. They probably have their age in there and easily identify what the population is going to be. So most of the time we're working with describing from a sample that we've taken and looking at the sample statistics. So the first part in descriptive stats, we mainly are going to focus on this column over here. We get into probability. We're going to focus on this population part. We're going to, what do we think the mean would be in the population based off of some patterns that we see in this particular scenario? And we can think about, like, well, what probably is the average? And going through. And then we'll tie them back together when we get to inferential statistics. Inferential statistics doesn't start until chapter 7. So we have a little ways before we get to that point. Now there's different types of data that we're going to measure. And we're going to start with the difference between like numeric versus categorical data and the terminology that we use. We have quantitative measurements or data. And think about this as our numeric data. I like to kind of shorten up the first part of the word and think of this as a quantity, just to help me to distinguish between the next one, which is qualitative. And then qualitative, think of quality. Qualitative data is a categorical data. You have some type of category. You could have a numeric value that represents a category. So don't think just because you see a number, it's automatically quantitative. If that number stands for something like yes, no, male, female, those kind of things, or a Likert scale, we'll talk about that a little bit, but when you talk about I strongly agree to disagree on a scale from 1 to 5, there are numbers there from 1 to 5, but they really stand for whether you agree with something or not. It's a little different than so be careful with those quantitative versus qualitative data. the data itself, whether it's quantitative or qualitative, is broken down a little bit further. So when we take our quantitative data here, it's broken out into two different types, and our qualitative data is broken out into two different types. And there's subcategories under this for the name. So if I'm looking at my quantitative data, the most common type of measurement, also called as levels of measurement, is called ratio. And when we're looking at ratio data, it's quantitative, and the main thing that separates it from the next category is that it has a true zero. And I put here 0 equals nothing, meaning that that's kind of a clue for myself. What do I mean by a true 0? It means that when the numeric value is 0, that there's nothing there. Like somebody's height. At 0, there's no height. At weight, there's 0 height. 0 degrees Fahrenheit. Is there nothing there? It's 0 degrees outside, or 0 degrees Celsius even. Is there no outside? It's cold, but it's there, right? So when we talk about a true 0, temperature, and at least Celsius and Fahrenheit, doesn't fall into the ratio category. Because that's an arbitrary scale that man made up on here. Now there is one that does have an arbitrary, has a real 0 at temperature. Anybody know that one? Kelvin. Kelvin at 0, there's nothing there. So that is one of the few that actually is a temperature measurement at ratio. IQ score, for instance. It doesn't make sense to have an IQ of 0. You're not even really alive, brain dead, or it just doesn't make sense on the context of the scale that we take intelligence quotients from. So it doesn't fall under the ratio. So those couple different weird man-made, usually, categories that we have that are numeric but don't have a true 0, we call those interval data. All right, then our qualitative data is broken up into two different ideas, and the ones that we're going to work with are nominal and ordinal. Nominal is some type of name. You have a word associated with it, but there's no order to it. So for instance, the color of your car. There's not one that says one car color is going to be ranked differently than the other colored car. Gender, for instance. There is no order to which it comes. There's many different nominal things like that. So think of nominal as just a name. And so that helps you just think of the word name. If those names have some type of obvious order to them, but they're not numeric on a scale on a number line where I can count them on a number line, then we call them ordinal. So think of ordered nominal values. What year you are in school. Freshman, sophomore, junior, senior, for instance. It's a label, but there's obvious an order. Freshman comes before sophomore, sophomore comes before junior. Likert scales, for instance, a lot of times will fall under the ordinal, where when you disagree to agree. Those kind of scales will fall under ordinal. Many times I'm thinking about this quantitative data in here. Almost all of the examples are going to fall under ratio. It's hard to come up with the interval example. Many of the things that you can measure are ratio data. So blood pressure, height, weight, age, all of those things are going to be under the ratio category because we're measuring those values. Quantitative data can also be broken out into what we call continuous and discrete. Put in here a measurement with no breaks from start to finish. The counting is kind of thinking of the discrete value. So you have some type of break on your number line between each one. And thinking of to myself, a lot of times these are hard because we're very used to answering questions as a whole number. Like if I say, how old are you? And you say 24 years old. You're actually not exactly 24 years old. You're 24 years old and how many months, how many days, how many hours, how many seconds old you are I can keep going out as long as I have a measuring tool good enough, and as soon as I measure it, it's instantly changed, right? You're now a nanosecond older, something of that sort. So in your head, I'm like thinking, oh, that's a number line, 23, 24, 25, just because we're used to recording that. But in a survey, there's nothing that could say that you can't answer 24, 25 years old if you're, 6 months into your year. So again, that would be continuous data. So thinking about it, did you measure it somehow? Did you get a ruler out? Did you get a stopwatch out? Did you get a blood pressure cuff on there? You are measuring it somehow. That's going to be continuous data. Your blood pressure doesn't instantly become a certain number. It goes up and down from the time you're born to the time you die. You're going through. There's constantly something there. It doesn't just instantaneously pop up to the next value. There's a change, gradual as it may be, from our measuring device. If I'm asking how many cars go through a drive-through, then we have 1 car, 2 cars, 3 cars, whatever going through. There's not half of a car driving through. Maybe I guess you could have halves in there, but at some point you're going to have a break in the number line. So we're counting how many cups of coffee that somebody drinks. You could have 1.5 cups of coffee, but it's again not a measurement of say how many. If I say how many ounces in that cup, that's different because now that's just as good as the measuring tool I'm weighing or measuring in liquid volume that I have. I mean, you can get that very, very precise and go out more and more decimal places with that. So one of the questions it'll ask you for in here, I'll give you a scenario and you have to identify if it's continuous or discrete. Again, just think about, am I measuring it or am I counting it? That's usually a good idea of how to distinguish between those two things. All right, we're going to jump into chapter 2 now. We're going to talk about some organizing tools, making tables and things that sometimes are helpful if you have a huge data set. We're going to be working with some really small data sets just to save time. You probably don't need to do this if I only have 5 items in my sample, but if you had 5,000 items in your sample, it's hard to look at the patterns within that. So we make tables and charts and graphs to help us with looking at these patterns. So one of the ones that we're going to look at is called a stem and leaf plot. Stem plot, stem and leaf graph, those are all the same type of thing that we're working with. Working with continuous data, and we want to be able to break up that data into different categories. So let's say I have some sample data. Maybe they're ages. I'm just going to make up some numbers I'm going through. And again, a very small data set. But if I were to make a stem and leaf plot for this, I would want to identify the smallest value in the data set, which looks like 18, and the largest value in the data set, which looks like 45. I'm starting with the easiest scenario where you only have 2 digits. This will look a little different if I have 3 or more digits in here. We're going to take our number and we're going to divide it up into 2 pieces. So again, it's really easy when you only have 2 numbers in here. If I were to split this 45 into 2 different pieces, the number on the left is what we're going to call the stem, and the number on the right is what we're going to call the leaf. All right, so we talked about the stem and the leaf. So I have a stem of 4 and a leaf of 5. And what I want to do is identify the smallest stem to the largest stem in my data set. And it's okay if you miss one, you can always add more later on. But I'm going to have a small stem of 1 and the largest stem of 4. And I don't want to skip any stems between that point. So even though I purposely didn't put in the ages in the 30s here, I don't want to skip the 3 on the number line. So think of this, if I were to turn this sideways, it's going to be like a number line counting by tens, 10, 20, 30, 40. I'm going to go through in order from the smallest value. Now, if you had a huge data set, you might want to just tick off each one at a time and then reorder them later, have a kind of a draft thing. Well, if you had a big data set, I would use a computer to generate this. I'm going through, I wouldn't be doing it by hand. But 18 is the smallest value. So what I'm going to do is take over here the stem of 1, I'm going to write in the leaf of 8 to the right of it, along that same row. And the next smallest value is 19. I'm just going to put a check mark by each one as I know I put it into my graph. So it gets a leaf of 9. You put a space or a comma. And then we have 20. Actually, I have 2 20s. And so I want 2 zeros represented there. I don't want to... Oh, is there 2 19s? Thank you. Left one off there. So you want an actual leaf for every single numeric value in the data. And then we have 21. What do we have next? 2 24s, it looks like. And then a 25, a 28, and a 29. And then the last one is 45. When I look at this, I could kind of imagine if I were thinking about this sideways, if I equally spaced these things out as a little bar graph. And so it can quickly tell me how the distribution is shaped, and we'll talk about distribution shapes in a second in here. But I can see that most of my ages are in the 20s, with a kind of a lump over here in the late teens, and then one person out here at 45. I'm going through. And this out here is going to be important. This value out here is called an outlier, because it's far away from the rest of my group. When you have these blank values in here with the number way off in here, what happens then is that my average will get pulled to those high numbers in there. So if I was to leave that 45 out, I would get a value that's much closer into the 20s here. If I put this value in, it might actually give me an average up into the high end of the 20s, if not early 30s in here. So we'll talk about what outliers do to the data set. The situation, I might want to go back and make sure that's not a typo first. If it is in there, then you have to think about, is a good sample, then we need to leave it in. We can look at other types of statistics that are not affected by outliers. The stem and leaf plot usually goes by tens. You could have it go by fives, and what you would have in that scenario, you have 2 1s, 2 2s, 2 3s, 2 4s, and you put the numbers from 0 through 4 in the first row, and then 5 through 9 in the second row on the stem categories. We're not going to do that in this class, just in case it comes up. And sometimes you'll have what they call side-by-side stem and leaf plots, where you have the same stem and you have group 1 coming out to the right on this side and group 2 coming out to the left on this side, so you can kind of compare them side by side on the same number line. Microsoft Excel does not do stem and leaf plots for you nicely, so just keep that in mind, that when it comes to homework, you may have to actually do this one by hand. Let's talk about the shape of data just real quickly, the distribution shape. So the first one, symmetric, and it can come in all forms, but the more common symmetric distribution that we will work with, is the bell shape. It's supposed to be like, if you're turning it sideways, kind of look at the bell of a trumpet, is where that word bell shape comes from. The middle of the distribution, if I didn't draw it perfectly, but if you were to put a line in the middle of the distribution here, you should get a somewhat mirror image from left to right. And we talk about usually it's approximately bell-shaped. It might not be a perfect mirror image, but it's pretty close to being a mirror image on either side. But you could have other types of distributions. For instance, it could be just a flat rectangle straight across, but this is your middle. Again, kind of thinking a rectangle on either side. You could have bimodal data, where you have some peaks on either side. Just if you can put a line in the middle and kind of get the same image on either side, that's what your symmetry comes from the symmetric distribution shapes. We call this one uniform. Bimodal, we haven't talked about the mode, but the mode is the most frequent value. And so there is 2 peaks to this value, thinking about the frequency being the height of each of these bars here. You don't need to know the specific little shapes, but you just need to know the symmetric part of this. Then we have skewed data, also called positively skewed or skewed to the right. And then the reverse of that, we'll look at negatively skewed and skewed to the left. The skewness is the direction of the tail, not where most of the data is. So we see this a lot in exponential decay. So if this is my x-axis and this is my y-axis, if I start at this point on the left and we have some type of decline within what's happening there. But it doesn't have to look like that. It could look like this. Could have a bell at the edge here. There's different things, but about where is the tail, and that's the direction it's skewed in. Most of the data is on the left, but we have some little outlier out here on the right-hand side that's skewing on the positive direction on the number line, skewing to the right on the number line. Just reverse those pictures and you get skewed to the left. Exponential growth, or something like this. A lot of my midterm grades look like this one. You have a cap on the score, can't get above that. Most people are in the A's and B's, and then you have a couple people that get D's and F's down in here.